Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In the last video, we were working on our Dequeue implementation. We're going to work on the Dequeue implementation in this video. One thing that needs to be added, though, is we wrote the Dequeue, but it has one factor missing, which is the fact that once we've added 9 things, the 10th thing is going to overflow our array. So we need to have the ability to make this larger. That's not a hard addition for us to make. We simply say if back is greater than or equal to heap.length, then we need to grow the array. So val temp equals a new array of heap.length times 2. We need to remember to set heap to temp, and in between these we will copy them over. And I actually don't need to copy sub-0, so I'll start at 1. Okay, so now our Dequeue will actually grow. So what about Dequeue? So you should recall that the procedure here is we're going to pull off this top element and we need to return that. So we can go ahead and add the code for that. We're going to remember the value at heap sub 1, and then we want to make sure that's the value that we give back in the end. In addition, after we have effectively pulled that off, we need to take the last element in here, kind of move it off into a temporary, and then imagine that there is a stone at the top that is going to settle down through, and it will stop either when it gets to a leaf or when it gets to the position where the element from the bottom is allowed to rest. So, the way we're going to write this code is we'll start off. So actually first let's make a val. I'll use the temp variable again, equals heap sub back. We also need to decrement back, and I will do that first. If I didn't decrement it, this would have to be back -1. The location of the stone starts at 1, and now we have a while loop. Now this while loop needs to go until we find a resting place, and basically there are 2 possible values for the resting place. One is that we've gotten to a node that has no children. So while stone times 2 is less than or equal to back. Back stores the location of the, actually no, so I don't need equals, just less than. That's one part of the condition. So we would stop if we get to something and there isn't anything below it. So if the child of that, the left child, so the times 2, is larger than the index of the last item, then we need to stop. Turns out if it's equal, this isn't the index of the last item, this is the index of the item that we've pulled up into our temporary. What about the other condition? The other condition is that that we've gotten to a place where both children are a lower priority than the thing that is settling down. Okay, and that, it turns out, is hard to phrase, because the fact that we know that we have at least one child from this first condition doesn't tell us, whether we have 2 children or one child, and we would need to use the larger of the 2 children if we had 2 children. There's a lot of logic in there. So I'm going to go ahead and introduce another variable that I called the flag. And we're going to keep going as long as flag is true, so I don't forget to do it later. Heap sub stone, once we're done, is equal to that temp value. Very similar to where we set heap sub bubble equal to what we're adding. So what happens inside of here? Well, inside of here we need to do two things. First, we have to decide if we should move further. And we're going to start by creating a variable that I will call smallest child. And smallest child is going to be stone times 2. Okay. I'm making the assumption here that the first child, the left child, is the smaller of the two. Of course, that might not be the case, but it will be the case either if it is the smallest or if there's only one child. So if the stone times 2 plus 1 is less than back, and let's do higher priority. Higher priority of heap sub stone times 2 plus 1 over heap sub stone times 2. If that's the case, smallest child plus equals 1. Okay, so let's make sure we understand what this says. So if there is a second child and that second child has a higher priority than the first child, then we increment this by 1, which basically means that the second child will be the smaller one. Now we have one more thing to do. If that smallest child, so if the smallest child is a higher priority of the heap sub, I've called it, how about we call this instead of smallest child? Well, let me finish this. Comma, heap, actually no, temp, then we'll do something. I want to go ahead and refactor this. I'll call it priority child. Smallest child works nicely when you're doing things based upon like a time, but this might not necessarily be time, so given the terminology we're using here, I'll go with the priority child. If the priority child has a higher priority than the value that is sinking down, then we need to take and set stone equal to priority child. Before we do that, we need to move the priority child up. Heap sub stone equals heap sub priority child. Else. Well, so what if we found the higher priority child, but it wasn't a higher priority than the temp value? Well, that means that we found the location where we can stop, and the temporary value can go at the current location of stone. So that means that I set flag equal to false. And that will cause our while loop to terminate, and then we will store this in and return the value that we had found originally. So that's the code for our Dequeue. We could run this through the same types of tests that we had done previously for our sorted linked list. And in fact, the simplest way for me to do this, I'll go ahead and copy everything, make a new Scala class, test heap, priority queue, paste, The only thing we need to change here is change this to a heap priority queue. Everything else should be happy. And if we run the test, oh, we have errors. Okay, so we'll come back in the next video and we will fix the errors that are popping up in this test.